Today on episode number 4, we take a look at Ohm's Law. We take what we've learned from the previous 3 episodes and we use volts, amps, resistance to learn more about the relationship. So what is Ohm's Law? Well, Ohm's Law states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. So if we bring over a sheet here, and let's just draw a very simple circuit. Let's just make this a resistor. We'll make this positive. We'll make this a negative terminal. We'll show that this is R, as we learned on the previous episode about resistance, showing that this is a resistance. Everything from even a wire has a resistance. It don't necessarily have to be a resistor, but we'll draw a resistor here. So this will be our V, our voltage. So this will be I, our current through the circuit from positive to negative. So we have a very, very straightforward circuit. So we want to show it. The current's the same through the whole entire circuit. So let's read through that again. Ohm's Law, it states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. So that means if resistance is the same and our voltage is the same, then our current will be the same. And they are proportional. So with that being said, we can actually draw a very familiar formula, which is known as Ohm's Law. V over I times R. Sometimes we can see the V represented with an E. So E for electromotive force instead of a V. This is the way I actually learned it. But this is the same as calling it V. So if you do see E over I times R is the same thing as V. I think it's more widely accepted today to use V because E can be energy, it can be some other things. As we get deeper into formulas, we'll stick with V over I times R. But this little drawing that I found on the internet, it just shows real easily. If you want to know the voltage that should be supplied to a circuit, and you know the resistance and the current should be in the circuit, where this current times resistance will give you voltage, which is what is showing here. If you want to find your E equals I times R, or your V, your volts. One simple way to look at this, even though it's very simplistic, if we were to have 1 volt and the resistance is 1 ohm, then our current will be 1 amp. And even though this is real simple, one thing I failed to realize when I learned Ohm's Law that I had to learn later on is 1 volt, 1 amp, 1 ohm. It's an important lesson here as we're learning this. We talked about in episode number 2 about measuring current. And one way that we done it was with a multimeter. And we mentioned a shunt resistor being inside the meter. Well, that's how this works. A lot of times these are like 0.01 ohm. But there is a shunt resistor across that we're going through when we're checking especially our 10 amp range. It's a very large resistor in there. That metal bar right there that you can barely see is shaved off a little bit for calibration purposes. It is across the 10 amp jack, and this 10 amp jack, the current actually flows through that shunt resistor, and it's a low ohms, but we actually get that reading, a voltage reading across that resistor. We kind of learn right here how that works. A 1 ohm resistor here with 1 amp is 1 volt. So if we didn't know this current, we could simply read across this resistor and be 1 volt, which would also be 1 amp. So just think about that in the future, that there's ways to check current by reading voltage if you know the resistance of what you're reading across. It's not uncommon at all to see a very low ohm resistor across a circuit for current feedback. Try to draw this a little bit better. Now let's say we have 10 volts, and this is a 2 ohm resistor, so we have 10 for our V. Our resistance, our R, is 2, so we got a psi for our I. So what is our I? Well, 10 divided by 2 is 5 amps. So Ohm's law is that simple. It's not hard at all to calculate. It's good to know when you're designing a circuit, the ohms, current, and voltage relationship. Go ahead and erase these back off. If we want to do another one real quick, and we'll stick with the 10 volts, it makes it for easy calculations. If we have 10 volts across, and we have a 10 ohm, then we're also going to have 1 amp. Just like when we have 1 volt and 1 ohm, we have 1 amp. Because once again, 10, and this is going to be 1 for your current. So Ohm's law can be relatively simple. It's beyond the scope of this lesson, but I do want to share, I found this on the internet. It's just a good way of showing the formula wheel. It looks a little more complicated, but it's not any more complicated really. It just has an extra spot called watts, or P for power. So we can solve for power, voltage, current, and resistance. Now once you understand this wheel, you can calculate even your wattage. Because if you want to solve for watts, and you know your current times your volts, then you can solve for watts. If you only know voltage and resistance, well then voltage squared divided by resistance equals your watts. So it shows you around this wheel the way to solve when you're missing 2 out of the 4. You can still calculate power, voltage, current, and resistance. So for today, this is as far as we really wanted to go with the formula part of Ohm's law. Just a little bit of learning about the formula, the relationship, and how easy it is to figure it out. And before we go, we'll just take this power supply and we'll look at it with a 1 ohm resistor. We'll simulate it with a real working load on it. So back now with a 1 ohm resistor. If we wanted to check this 1 ohm resistor, I would get my 179 out, and we could still do it with the 179, but it don't have the relative mode. So either I could use this little BK Precision, does have a relative mode, where we can zero out the leads. This one, the Fluke 87, also has a relative. This is actually one of my earlier Fluke 87s. So because this is a very low resistance, and we want to be as close to 1 ohm as we can get, what we'll do is we'll read, and it does read very close to 1 ohm. We put the leads together, it's showing about 0.2 or 0.3. If we want to get real precise, we can hit the relative. The triangle will show up on the screen also. and that gives us a little bit better measurement. So one reason I brought in the 87 original that I had was kind of just to show the resolution difference, and it's still a good working meter. I had it a long time, probably over 20 years. But this is an 87.3, a very similar meter, just a third generation. So if I want to take it and do the same test, seems similar enough. It also has relative mode, so I can also compensate for it. So although it does seem very similar, it does also have a 4.5 digit 1 second. It's a little bit more resolution. I probably got to redo the compensation, but now we see we have an extra digit here, so we do have a little bit more resolution. So if we go ahead and compensate now, see our delta. We see that we do have a little bit more resolution this way. Should also mention that something like this Esr meter is a really good way to check something with more precision and something that's low ohms. Because if you are getting down to something where you need precision, you need to buy a precision resistor. And of course, a regular meter, even if it does have relative mode, it won't get down quite as low as these. You can zero them out. You can check for true zero. And I think this one goes down to 0.025 maybe. Yeah, I think 0.025 is as low as it'll go. But that's still pretty low. So if we look at the actual resistor we're checking with, it's not a precision resistor, but we see that it is relatively close, just for testing and showing for an example today. It's right at 0.9, so 0.91. I just thought I'd share that. Of course, ESR meters typically are good for your lower ohm scale. So if you do have one available, it can help a lot with checking your low ohm resistance. So now with our 1 ohm load, now we have our power supply on 1 volt. Alright, so now I'm going to put the load across. And we see how we're very, very close to being 1 amp. We got 1 volt, 1 ohm, and 1 amp. It's always important to use the right wattage resistor for your load. Now this is only a 1 watt. If we remember from our circle, if we do our current times our voltage gives us our wattage. So we want above a 1 watt resistor for this, which we're well, I believe this is a 5 watt, it's barely getting warm. We want to check our voltage here. If you look, our voltage is almost identical to what our current is. And that's because this resistor showed us it was about 0.9 ohms, which is showing about right. So now we can take a little more wattage with this. So now let's bump it up. Let's bump it up to 2 volts. I gotta take my current up a little bit. So now at 2 volts, we at 1.88 amps, and the voltage across the actual resistor at this exact same point. Because remember, this 2 volts is from here. So we got some drop here with this load. So measuring the exact same point here, we're showing identical. And this is voltage. So as long as this is a 1 ohm resistor, then the voltage across is going to also show the current. As we go on up some more, 3 volts is about as high as I want to push it, but you see that our voltage is showing our current still. So that's just a good example of Ohm's law and how it can help us out in a circuit. And it can really come in handy when we're looking at oscilloscopes. I actually do not have any type of current probe for my oscilloscope, but with this little 1 ohm resistor, I really don't need one. If I'm interested in a circuit and want to know the current, as long as I have this 1 ohm resistor in line and it can affect the load of the circuit I'm dealing with, I can check across it and plot my current as a voltage and just chart it over time, just like I can my voltage signal. Well, I hope you liked this video today on Ohm's Law. If you liked it, please give it a thumbs up. Please subscribe, and thanks for watching.